Hi, today we will discuss one topic in compiler design, left recursion, and we can study what is a left recursion and what is the problem of left recursion and how can you remove left recursion from a grammar. First I will define what is a left recursion. Let a grammar G is equal to VTPS is said to be left recursive, then there is a non-terminal A and A derive plus A alpha, where alpha is a string. Alpha is a string formed by using terminals and non-terminal symbols. And look at here, A is a non-terminal. A derive a string of the form A alpha, where the leftmost symbol in this right side is the same non-terminal A. So if there exists such derivation in the grammar G, then we will call G possess the property left recursion. And one example I will show you. Let us see this grammar. S gives A or B, A gives S, C or D, and here you can find the non-terminals as S and capital A. These are the two non-terminals, and terminal symbols are small letter A, small letter B, small letter C and small letter D. These are the terminal symbols and these are the non-terminal symbols. And I can derive a string of the form S gives S derive plus S C A. That is S first derive capital A, and I replace this A by S derive S, C and A. So in short we can say that S derive by using more than one steps S, C, A. So here you can see that left side symbol is a non-terminal S, and in the right side of the derivation the very first symbol in the left of the right side portion is also A. So you can say that this grammar possesses the property left recursion. And there are different type of left recursion you can see in a grammar. And first type is immediate left recursion. Left recursion. And first I will define what is an immediate left recursion and how can you remove immediate left recursion from a grammar. Suppose if a grammar G is equal to VTPS has a production of the form A gives A alpha or beta, and here A gives A alpha where A is a non-terminal and alpha and beta are strings formed by using terminals and non-terminals. And this is, here you can see this is a production which is present in the grammar G, and here left side of the production is A, non-terminal A, and the right side, the leftmost symbol in the right side of the production is also A. So if such a production is exist in the grammar G, then we can say that G is immediately left recursive grammar, because here we saying that the grammar has the property immediate left recursion, because in the production itself what it is left recursive. So we can remove this immediate left recursion very easily. First I will give one example how we specifically remove immediate left recursion. Then I will tell what is the general rule to remove immediate left recursion from a grammar. See, let us see here, this itself is the production which is present in the grammar G, this grammar G. Then how can I remove it? See, before finding the equivalent grammar, so I will tell you what is the problem in this grammar having production A gives A alpha or beta. See, suppose I am going to construct a parse tree where its root is A. Then I have two choices. One is I can replace A by A alpha, or I can replace A by beta. So look at C. Here I am replacing A by A alpha. And another choice is A gives beta. Okay, if I replace A by beta, then my string is beta itself. And here if I replace A by A alpha, again non-terminal will come, so I need to replace again A. So either I can use the production A alpha, A gives A alpha, or A gives beta. So suppose I am using A alpha, then I will get A alpha, or I can replace this one by beta. If I am using beta, then the language, the string is the parse tree string that this grammar is derived is B alpha. If I am not using beta, then again I will get a non-terminals in the left side. I need to replace with A either by using A alpha or by using beta. So this will continue. You can see that in the parse tree, the leftmost node is always non-terminal, and if you are using this, removing this non-terminal by using A alpha, then it will continue in the leftmost direction. It never will end. If you want to end, the only one option is replace A by beta. This is the only one option. So in general, you can say that this type of parse tree will derive what B in any number of alpha. If it is 0 number of alpha, you will get this parse tree. If 1 number of alpha, you will get this string, that means up to this portion. And if it derive 2 number of alpha, like B alpha alpha, you will get we can derive from this parse tree itself. If it take 3 number of alpha, etc., etc., that means the alpha star indicate that n number of alpha you can use. So at least one beta will definitely come. That means if a grammar has a production of from this one, then that derive the language L is equal to beta alpha star. And since suppose you are using a parse tree construction by using top-down parser, then top-down parser will start the construction of parse tree from top to bottom. So this type of parse tree it will construct. But you can see that if such production is there, it never will end if you are replacing A by A alpha. and the only one option is if you want to stop the past reconstruction, you have to replace A by beta. So we have seen that the language of the grammar having the production A gives A alpha or beta is L is equal to beta alpha star. Then by knowing this language, here left side is both non-terminal. By knowing this language, very easily you can find the equivalent production corresponding to this one. See, at least one B is there, so I need to write beta followed by A dash. That means one beta, this beta is okay. Then A dash will derive alpha star. That means A dash needed to derive alpha star. So for that purpose, my A dash is alpha A dash. So we know that alpha star contain empty string, so that's why epsilon also I will include. And what is A dash? A dash is a new non-terminal. So you can see that this is the production having the property of immediate left recursion, and that is replaced by using this tree production, like the way you can remove immediate left recursion. Okay, then one example, E gives E plus T or T. So here you can see that this is a famous production. It's a part of our arithmetic expression grammar. So here left side is head of the production is E, and in the right side, the leftmost symbol on the right side is also E, and so you can see that this is A, this is also A, and this is, we can call it as alpha, and this is our beta. Then this production you can replace by using above production, like E gives T E dash, and E dash gives alpha A dash. That means alpha is our plus T E dash, then finally one epsilon. This is the equivalent. This is the equivalent production removing left recursion, immediate left recursion. Here E dash is a new non-terminal. New non-terminal. So this is the general rule how to remove left recursion from a grammar. I will tell. Let us see. If you have a production of the form A gives alpha 1, A alpha 1, A alpha 2, etc., etc., A alpha n, then beta 1, beta 2, etc., etc., beta em. So how many en A productions were all are left recursive? Then em A production with the right side is beta 1, beta 2, etc., beta m. So total number is here m, here it is en. Then what is the equivalent production which will remove immediate left recursion. A gives beta 1 A dash or beta 2 A dash or beta 3 A dash or etc beta M A dash. Then A dash gives alpha 1 A dash or alpha 2 A dash, A dash is all or A dash, etc or alpha n A dash, finally epsilon. This is the general rule how to remove immediate left recursion if you have such production which is present in the grammar. That's about immediate left recursion. And suppose you have recursion but it is not immediate. From the definition from the beginning itself, I told you the grammar S gives A or B, A gives SC or D, is left recursive, but there is no production having immediate left recursion, showing immediate left recursion. No production, but it is left recursive. So we have seen that yes, we can derive SCA, or in another way we can say A also will derive AAC. That is, A derive SC, then capital SC, then A derive, then S we can replace by A and C. So you can see that here A, that is A derive plus A CC. So this is also according to our definition, this grammar is left recursive. So this also will create problem. So the same example where we have seen that this also will create problem. So how to remove such type of left recursion which is present in the grammar? There is an algorithm. That algorithm will help you to remove left recursion, whether it is immediate or any other sort of left recursion that we can remove. Let us see this algorithm. I will briefly explain. Very simple algorithm. The statement you can see here. So this algorithm will help you to remove left recursion, whether it is immediate or indirect left recursion we can remove. So let us see. First step is step 1. So arrange non-terminals present in the grammar in some order. Like you can any arbitrary order. It is not restricted in any particular way. It is arbitrarily you can select the non-terminal and you can order it. So order may be like A1, A2, etc. AN. Suppose AN non-terminals are there, then you have to order it in A1, A2, A3, etc. AN. The step 1. In step 2 is then you can find how many non-terminals are there. So here n non-terminals are there. Then you have to start a for loop where I ranging from 1 to n. Do the following things. Then step 3 is J, another for loop, inner for loop, which is inner to the first for loop, where J is from 1 to important 1 to J minus 1, and do the following things. So step 4 is replace each production of the form where AI gives AJ gamma, where we know that I is always greater than or equal to j, because j value is ranging from 1 to I minus 1. So we can say that I is always greater than j. It's not equal, even if equal also will not come. If you have such production, such type of production is present in your grammar, you can replace that by ai gives alpha 1 gamma, alpha 2 gamma, etc, etc, alpha k gamma, where aj gives alpha 1, alpha or alpha 2 or alpha 3, etc, etc, alpha k. Nothing we will find. Suppose such type of one production, this type of one production we have seen in the grammar, then we will find what are the aj productions. Aj production we will find aj productions, then all such aj production we will use to replace j. So that is what happened here. Here we have replaced j by its corresponding right side. So gamma is same, there is no change. So suppose you have k number of aj productions, then all such right side of aj production we have used it to replace by aj. This is called expanding, actually nothing, very simple expansion, because aj is equal to alpha 1, aj equal to alpha 2, etc. So that's why here first we will use alpha 1 to gamma, then alpha 2 to gamma, then alpha k to gamma. So this is what in the inner for loop. Then by doing this one, our for loop will end. Then you have to come out of the inner for loop and you have to do eliminate immediate, very important, immediate left recursion among ai productions. By doing this expansion you may get immediate left recursion, and you have to remove all immediate left recursion by using our general rule that I already talked. Then this is in what outer for loop. So do this operation, remove the immediate left recursion, then when we termination condition occurs you can come out of the for loop, both the for loop, and then you can stop it. So this will remove immediate as well as indirect left recursion. For example, see this is the grammar that we have used for defining left recursion. See, S gives A or B, A gives AC or ST or F. These are the productions present in the grammar, where we know that S and capital S and capital A are the two non-terminals. So there are two non-terminals, so capital S and capital A. So I have ordering these two non-terminal in form A1 and A2, where A1 is S, A2 is capital A. So A1, A2 is SA. So I am rearranging this above grammar by A1 gives A2A or B, then A2 gives A2C or A1D or F. This is what step 1. Step 1 is over. Here it is telling that you have to arrange the non-terminal in some order, A1, A2, etc. AN. Then after arranging you will get a production. A1 gives A2 A, etc. Then we will start our for loop. There are two for loop where we can say that I value is ranging from 1, then j value is 1 to I minus 1. So 1 to I minus 1 is 0, so there is no j value. So then I will increment I equal to 2, then j equal to 1 to I minus 1, I1 minus 1 is 1. Okay, then the fourth step telling that you have to replace, if you have a production of the form A2 gives A1 gamma. We will check it if you have a production of the form A2 gives A1 gamma. Yes, you can see that there is one production. Here you can see A2 gives A1D. So that satisfies this condition. A2 gives A1 gamma. Okay, then we will replace that by first we will find what are the A1 productions. A1 productions are A2A or B. These are the two A1 productions. Then this production we will replace as A2 gives, where our gamma is, you know that gamma is equal to D. So this is A2, this is A1, this is gamma is D. So then A2 we will replace as A2 gives A2A D, B and D. So these are the two production after expansion. That is nothing, just we will replace A1 by these two values, A2A and B, nothing else. Okay, that is what we did. Then your J value can't increment because J will moving from 1 to 1. Then I value is reached the end, I is equal to 2. Then we will come out for both the for loop. Sorry, we will be in the fifth step. Fifth step is if you have any immediate left recursion, then we will check it. Any immediate left recursion is there. All production we will write. Productions are A1 gives A2A over B, then A2 gives A2C, and A1D will be replaced. A1D we replaced as A2AD, BD and F. Okay, these are the productions after finishing fourth step. Then fifth step is removing immediate left recursion. So here A2, here A2, then again here also A2. So two production having immediate left recursion. So these two are the beta. So very easily we can replace by using A2 gives BD some A dash, F some A dash, then A dash gives, this is alpha, C into A dash or AD into A dash and epsilon. So okay, so total productions is R. So finally I will write what are the total final productions. A1 gives A2A or B, A2 gives BD A dash, F A dash, and A dash gives C A dash, AD A dash or epsilon. Then you can replace A1 by S and A2 by A. Then A dash is the new non-terminal. So the final one is A1 is S. So S gives A2 is A or B, and A2 is A2 gives BD A dash, F A dash, then A dash gives small letter C A dash, AD A dash or epsilon. So this is the final grammar where we